Solving general chemistry problems. Electrochemistry. Form cadmium and chromium into a galvanic cell. What is the standard cell potential? What's the overall chemical reaction equation? What's the standard Gibbs energy for the reaction? What is its equilibrium constant? Here we have the relevant standard reduction potential data. By now you should be able to determine the cell potential and the overall reaction equation. But we now need to tie back into the section on thermodynamics and see how these measures of potential, which seem to be telling us about how reactions proceed, relate to the Gibbs energy that we found previously to hold the key to understanding reactions. If you remember back to your introductory physics classes about electricity, the electric potential difference between 2 points, also called voltage, in an electric field is defined as the work done per unit of charge when moving a test charge between the 2 points. Work has units of joules, and charge has units of coulombs. So this voltage has units of joules per coulomb, and that unit is called the volt. When an amount of charge in coulombs, Q, moves between a high potential and a low potential, V, work in the amount of Q times V is involved. In an electric circuit, the total charge Q that is transferred is related to the total number of electrons, Z, that are transferred times the charge per electron. The electron charge is one of the most fundamental constants of nature. It is 1.602 times 10 to the minus 19 coulombs. For example, if 1 times 10 to the 24 electrons are being transferred, the total charge is a bit more than 160,000 coulombs. When dealing with electrons, it is easier to measure them in moles. The charge per mole of electron is given by a constant F known as the Faraday constant after Michael Faraday. Its value is 96,495.33 coulombs per mole of electrons. Sometimes you will find it rounded off to 9645 and sometimes even rounded to 96,500. If we convert that 1 times 10 to the 24 electrons into moles of electrons and use the Faraday constant, we get the same 160,000 coulombs of charge being transferred. We can quantify the number of eggs we purchase at the store by saying, I bought 30 eggs, or by saying, I bought 2.5 dozen eggs. We can do the same with electrons. We can say 1 times 10 to the 24 electrons pass through this circuit, or we can say 1.66 moles of electrons pass through this circuit. We choose the most convenient unit. Moles often helps us to get rid of large exponents when dealing with the large numbers involved in chemical processes. We can measure charge using the charge of an individual electron, or we can use the charge of a mole of electrons. Most conveniently, however, Q, which is the charge to be measured in coulombs, is equal to N in moles times F, where again F is the Faraday constant. The equation Q equals NF is important to remember as it connects the number of electrons to the charge transferred. When that charge moves through a potential difference V, the work done is W is equal to NF times V. This work can be specified to be electrical work. Now this is in contrast to pressure-volume work studied in thermodynamics. The reaction in the cell may involve the formation or consumption of gases, and there may be some PV work involved. The electrical work, however, is separate. You can perhaps recognize here that this electrical work is equal to the change in Gibbs energy, for we can now recognize that delta G is the non-pressure volume work that a system can accomplish. In fact, the negative of delta G is the electrical work. So think of an electrochemical cell. It has a potential which we represent with E, so when it is operating to produce power, work electric is equal to NFE. And we can write delta G is equal to minus NFE. If the reaction is occurring under standard conditions, we'd naturally write delta G naught equals minus NFE naught. So how do we count electrons? Well, obviously we don't. What we can measure, however, is the current that flows in an electrical circuit. A current of 1 ampere is flowing when 1 coulomb of charge passes a fixed point in the circuit in 1 second. This is an exact definition. By measuring a current and time, we can calculate coulombs of charge. Current must be measured in amps and time in seconds in order to give charge in coulombs. So measure a current in amps and the length of time in seconds it is flowing, and the product gives you the charge in coulombs. Then, by using the Faraday constant F, we can find the number of electrons involved, measured in moles. The appropriate redox equation gives the stoichiometric relationship between electrons and any atomic or molecular participant, which allows us to find the moles of that substance from the moles of electrons involved. It is possible to, in the middle step, use the charge of a single electron and convert coulombs into the number of electrons, not measured in moles, just the number of electrons. But in general chemistry, this is not usually followed. Stick with measuring things in moles. One place students occasionally slip up is with the time. It must be measured in seconds. So if the question gives time in minutes, hours, or days, one must convert to seconds to find charge in coulombs. When we bring the voltage or potential into the discussion, it combines with the charge to calculate changes in the Gibbs energy of a process. Here is a good opportunity to emphasize again the importance of watching your units and let them guide your calculations. Look at the N in this equation. Sometimes it refers to the moles of electrons that have been transferred. Perhaps you let the cell run for 10 minutes while delivering 1 milliamp of current. In such a case, the Gibbs energy of the system will have decreased by some amount. You would have to have known the potential E, and that decrease in Gibbs energy would have units of joules. Another approach, however, is to discuss a particular reaction. When the reaction equation is balanced, the number of electrons, N, exchanged in that reaction is, as written, would have units such as moles of electrons per mole of reaction events. Then the calculation would produce units for delta G to be joules, or kilojoules, per mole of reaction events, which is the Gibbs energy change for the reaction. We might write it as delta sub Rg. This is a good time to return to the question we encountered at the beginning. We proposed a cell based on cadmium and chromium and want to determine the standard Gibbs energy change for the reaction. Cadmium has the most positive, and in this case the least negative, standard reduction potential, so it will be the cathode. Chromium therefore will be the anode, and oxidation will occur. Note also that there are different numbers of electrons transferred in the two cases, because the oxidation states of the two metals are different. Multiply the cadmium reaction by 3, the chromium reaction by 2, add them together, and this produces the balanced reaction equation. Even though electrons have cancelled out, this reaction, as written, represents the exchange of 6 electrons between the 3 cadmium atoms and the 2 chromium atoms. The standard cell potential, cathode minus anode, is plus 0.021 volts, or 21 millivolts. With this, we can determine the standard Gibbs energy change for the reaction. It is minus NFE0, which is minus 12.2 kilojoules per mole. Now look at those units. This is 12.2 kilojoules per mole of reaction events. But chemists generally leave off the lengthy descriptor of reaction events. It is just assumed that we know that given the context. This means that when this reaction occurs 1 mole times, as written, then the system's Gibbs energy decreases by 12.2 kilojoules. It also means that 6 moles of electrons are transferred from the anode to the cathode. And what about equilibrium constants? Well, recall from thermodynamics the relationship between standard change in Gibbs energy and K, the equilibrium constant. We can substitute the minus NFE0 for the delta sub Rg0 to establish this relationship between K and E0. And this relationship can be rewritten in various ways. You can do that to satisfy the specific demands of a particular problem. For the question at hand, the cadmium-chromium cell, which transfers 6 electrons per reaction event and has a standard cell potential of 21 millivolts, we find that K equals 4.9. The reaction proceeds forward, so the equilibrium should lie towards the product side. In comparison to most reaction, this equilibrium constant is really quite close to 1, but it probably should have been expected since the standard cell potential is so small, though still positive. Watch units in these calculations. Use cell potential in volts and the gas constant R in joules. If the question does not specify a temperature, go ahead and use 298 Kelvin.